Welcome to AP Calculus Review Part 3, where I'll be going over integration. So first let's try to understand what integration actually is. In short, it's the area, it's going to be the area under your curve. It's going to evaluate the area between your function, your curve, and the x-axis, or it could be the y-axis, depending on what you're doing. So the reason that integration is important is, let's say you have this function right here. This is our rate of change function. This is like a derivative. And given our rate of change, we can use integration to find out our accumulation of change, or it's supposed to be called our net change. The accumulation of change, it can be either like positive or negative. Let's say this is miles per hour, right? And our x-axis, this is going to be in hours. And so let's say like we're going forward here, we're going backward at this point, forward at this point, right? And we can use that, just our miles per hour, to figure out exactly how far we've traveled using integration. Since area, you take our miles per hour, multiply it by our hours, and this gives us miles. This could be, so that's how like your units would work. You'd be multiplying your 2. That's mostly what integration is used for, is to get this accumulation of change from a rate of change function. This could be like feet per second times seconds equals feet, stuff like that, right? So first, let's cover Riemann sums. I'm going to draw a function here. Let's make it look like this, right? Right now, how about there? So I'm going to start drawing some rectangles to approximate the area under this line right here, under this curve. So the Riemann sum is just an approximation of your area under the curve. So I'll explain exactly what I'm doing here. This right here is a left Riemann sum, adding together all of these rectangles gives us an approximation for the area under the curve. The reason why it's called a left Riemann sum is because the left side of all these rectangles is meeting the curve. So we're taking like our y value here and just like multiplying it by, you can call this like delta x. We're taking our y value, multiplying it by delta x, and we're doing this continuously over and over again for multiple delta x's. So like a y value here, multiply it by delta x, and so on. So we get this approximation. It's called our left Riemann sum. Now I'm going to do the same thing, but with a right Riemann sum. So what that would look like, it looks something like this. So you can see with the right Riemann sum, it's the right, say, corner of these rectangles is touching the curve. So this is another approximation of our area under the curve. Now these can be either underestimations or overestimations depending on what you're doing. So see that our left Riemann sum, this is an underestimation of the true area because you have all these little areas right over here that are not being covered by a Riemann sum. This is an underestimation because our graph, our function is increasing. Same thing here, but with the right Riemann sum, this would be an overestimation because the graph is increasing, or our f is increasing, right? And you see that there's all these extra areas above the curve that would make this more than the true value of this like area here. If it was decreasing on the other hand, let me just draw a quick picture right here. If it was decreasing, then it would be your left hand, your left Riemann sum would be an overestimation. And your right Riemann sum would be an underestimation. So it's important to note how left and right Riemann sums can be used to approximate the areas under the curve and whether they're under or overestimates. Does it go with left Riemann sum? This is for your right Riemann sum. The midpoint Riemann sum is, in most cases, it'd be a bit more accurate. And I'll draw the same curve here again. But this time, instead of the left or right corners touching the curve, it's going to be like the top middle touching the curve, or the midpoint of your rectangle. So look at midpoint right here, midpoint like right here, and right here. And this is like another way to approximate the area under the curve using a midpoint Riemann sum. So let's say if I had like an x value of a 1 here and I don't know 3 here, then I would take the value of the function at 2 and use that to make this rectangle for the Riemann sum. And finally, I'll go over a trapezoidal sum. With the trapezoidal sum, we'll start having trapezoids to approximate the area under the curve. So start drawing some here. You can notice how it's an even better estimation of our area under the curve. So do keep in mind the formula for a trapezoid is going to be your, we'll call this delta x, but for a formula it's going to be considered to be b, or base. So it's going to be b over 2 times your first side plus your second side. Here's what we call your like heights, your height 1 and 2. In other words, we're basically taking the average of these two heights. This can also be written as like h1 plus h2 over 2, which is our average of our two heights, and multiplying it by our base to get the area for this one trapezoid here. So it's 4 ways you can use Riemann sums to approximate the area under the curve. Now I'm going to go over integral as a sum. So basically what the integral is, this is like the true area under the curve. And so if I have this curve again, I can use like a left Riemann sum to approximate, right? I can use these like big rectangles. But if I start making the rectangles smaller and smaller, right, then I start to get even closer to the true value of the area of the curve. Like see these very small like errors here. These ones are like much bigger errors. So what the integral does is it uses an infinite amount of rectangles, and each of these has an infinitely small delta x. Because it's infinitely small, we call this dx. So d means like a very, very tiny bit, like the most, like an infinitely small amount of x. Each of these little rectangles here have an infinitely small width. So I can write this formula here. The integral from a to b, so you can make like this our a, here, like, and like this our b. This represents two like x values of f of x dx equals the limit as n approaches infinity of the sum from, let's use I, from I is 1 to n of f of xi times delta x I. So what this formula means is that this is our integral, and this represents our Riemann sum. It's just that the integral is a Riemann sum with an infinite amount of these like rectangles, and our delta x is infinitely small, and that's what this dx here represents. So your infinitely small width, or your base of these like rectangles, and your f of x sub I, that's like your y value, right? So like the y value here, the y value here, the y value here, so on. And so you can, it's important to know how to convert integrals and Riemann sums back and forth. So let's just say, for example, here from 3 to 6, Then you go from 3 to 6 of square root of x plus 2 dx. Right? And we can convert this to a Riemann sum by first starting out with our framework. Our limit as n approaches infinity from I equals 1 to n. This I could also be k, it depends. It really doesn't matter, it's the same idea. So now we start with our f of x sub I. So you're going to plug in our function here. Just going to have plus 2. I'm going to leave some more space. We'll leave the x blank for now. And then multiplied by our delta x sub I. We should also leave that blank for the time being. So, write these formulas down as well. X sub I, that's going to be A plus K delta X. Your delta X is equal to B minus A over N. So let's start with the delta X first. This is our distance between our B and our A. So it's like this. This is the distance which you want to take the integral of, or like this is the interval along which you want to take the integral, right? And we're dividing it into n sub-intervals, or n rectangles. So let's take our B minus A, which is 6 minus 3. That's just 3 over n. So the next step is deal with our x sub I, which is A plus K delta X. So let me just go over this real quick. You get 3 over n. This is like saying 3 over infinity, because we're dividing our 3 units, which is from 3 to 6, into an infinite number of rectangles or sub-intervals, right? I'm going to put some parentheses here. So the right now I should replace this with I, because we're using I in this situation. But you could also use K if you wanted to, because some people teach it like K, some people teach it like I, but I'm going to use I because that's standard for sums like these. For x sub I, we're going to plug in our A, which is 3. That's our like lower bound. Plus 3i. That was terrible. 3i over n. I could just like simplify that out. This is usually like 3 plus here, so 5 plus 3i over n times 3 over n. Alright, now we're done with that. So notice how the original function relates to the Riemann sum. You have the square root of x plus 2, square root of x, this can be considered x plus 2, and there dx is represented by this 3 over n here, where this I here is helping you find your like your y value, and 3 over n, this is just declaring that you have this infinitely small width. Alright, moving on to integral properties. So, start writing down the integral of anything from a to a, which is like, let's say like 0 to 0, or 1 to 1, or 1,000 to 1,000, is always equal to 0, because what you're doing here is, like, if you have your function and this is a, like, you're taking the area between this and this. There's nothing to take the area of. You've a width of 0. It's like going from your room to your room. You're not going anywhere. That's 0, right? You can reverse your integral bounds by negating the integral. So you have the integral from a to b of f of x dx is the same as the negative of the integral from b to a of f of x d of x, or f of x dx. So in other words, if you're taking the integral from a to b, and that's just you're going from a to b, and you're just taking the area as you go. But if I did the same thing from b to a, that would actually give me a negative value, because I'm like working backwards. Right? And so putting this negative here helps cancel that out. Reversal of your integral bounds can be useful in some like future problems. You can split up an integral into two separate integrals. Because remember, like, you're taking the area under the curve. So say from a to b, right? It's like we have the straight line segment here. This is nice and clean. We have this like curve here. So we can just like separate these, have this value called c, and say like this whole area from a to b is the same as the area from a to c plus the area from c to b. And that's another useful property of integrals, is that you can just split them up into smaller integrals, which may be easier to solve in certain situations. If you have a like constant inside an integral, then you can just like take it out. Right? Same with derivatives and limits. You just take the constant out and multiply it that way. And the last thing, you can add integrals the same way you add derivatives and limits. And it also works the same way if you're subtracting them too, right? Nice and simple. Okay, there's something else I want to cover. If you have a graph that's not continuous, you can still take the integral of it. You can just split this up into two integrals. So we call this our A, our C, and our B. You can split up this A to B integral into an A to C and a C to B. And you just take it that way. It doesn't necessarily have to be a continuous function for you to take the integral of it. And also, I'll start going to the actual math behind the integrals now. But before I do, I want to note the semicircle equation. The equation for a semicircle is the square root of r squared minus x squared. So you may find it as like 4 minus x squared, right? Square root of 4 minus x squared. Using AP calculus techniques, there is not a way to solve this numerically using the AP calculus techniques. So what you need to do for a semicircle equation, this is really important, is you just need to recognize it and be like, oh, this is a semicircle, so you should use the formula for a semicircle's area. And that's how you evaluate that. This really trips some people up sometimes, so I want to cover that. So let's say this is 4 minus x squared. Square root of 4 minus x squared. I want to take the integral of that from a negative 2 to 2. So take like the area under the curve. I can't solve this numerically, but I can recognize this as the area of a semicircle. Oh, so that's 1/2 pi r squared, which is 4. That would just be 2 pi. Yeah, so that's important to remember. Now let's move on to antidifferentiation, also as indefinite integrals. So an indefinite integral doesn't specify any like bounds here. There's nothing there. That's called an indefinite integral, or what we need to do is we need to find the antiderivative. That's what this empty integral sign means. It's usually indicated by a capital F of x plus c. And this plus c is any constant. And it's important when you're taking antiderivatives, because remember, when you're taking the derivative of something, your information about any constants is lost, because the derivative of any constant is 0. Like this could be 1, this could be 100, 1,000, and when you take the derivative, that information is lost. See, when you take the derivative, it goes to this here, this f of x. Now, to bring back that information, I add this plus c here to say like, oh, this could be anything. This could be 0, this could be 1, it could be -1, it could be 1,000. You never know, but that plus c is important because it shows that like information you've lost is not just gone forever. You bring it back when you're taking the antiderivative. This could also be written like f prime of x equals f of x. So the derivative of this capital F is this lowercase f of x. Or the capital F of x equals the integral from a, which is some number, to x, of f of x. This a usually helps you find a plus c. So do you want to mention that integration is a lot more complicated than differentiation. Any function you can think of, if you just like take the derivative of it, then it always has like a set. Let's call it negative, right? It always has a set derivative. It's really easy to find. But if you want to take the integral of a function, some of these, there really is no numerical, like elementary way to get an antiderivative for this. So it's important to like understand that not all functions can be integrated just using like these AP calculus techniques. It's more complicated, and it's something maybe covered in like higher level math, or maybe not at all. Sometimes they have like special functions just for these, because there really is just no real answer. You know what I mean? So the way to find an indefinite integral usually is going to be using the reverse power rule. So remember, the power rule just helps you find derivatives. The reverse power rule helps you find antiderivatives. So notice that for derivatives, when you're using the power rule, you take your exponent, multiply it, and then you decrease it by 1. Here, what you're first doing is you're adding 1 to the exponent, and then you're dividing it by that exponent. So you're adding first, and then you're dividing. So let's quickly take the antiderivative of x squared. The derivative of x squared is really easy, right? You just bring out the exponent, 2x, and we'll decrease it by 1, so it'll just be 2x to the 1, right? But for the antiderivative of x squared, you would first increase the exponent by 1, and then you divide it by that exponent. And don't forget, when you're doing an indefinite integral or an antiderivative, you have to add a plus c. Let's get started on the fundamental theorem of calculus. The first part of this is deriving integrals. So we write an equation for this. The derivative of an integral from a to, we'll call this u. Or no, not u. Let's call it g of x. Of fx dx. So remember that derivatives and antiderivatives, they're opposites. They'll like cancel each other out. But you can't just like completely ignore this part and just be like, oh, so it's just f of x. No. If you have something as your g of x here, like 3x or x squared or whatever, something like that, they'd just be equal to your fx times your g prime of x. So say when I take the derivative of the integral of, let's say 4, from 4 to x cubed of f. Well, it's actually not completely correct to say x, as you're going to use t. Because they're supposed to just be plugging the x into here. F of t dt, right? It doesn't actually matter what this variable is as long as it's not x, because you can't use x twice. You have it right here, you can't use it right here again. So you're just using t instead. What are we doing? Let me actually put something for f of t. Let's call it 5t to the 4, right? So what I do is you replace the t with an x. Now, 5x to the 4. Oh wait, no. Made a little mistake there. F of g of x times g prime of x. This looks really familiar because it's similar to the chain rule. So we have 5 times x cubed to the 4 times 3x squared, the derivative of that. So you get 3x squared times 5 x to the 12, you get 15 x to the 15. Right, and that's our like derivative of an integral. The next part of the fundamental theorem of calculus is about net change. It states that the integral from a to b of fx dx equals f of b minus f of a. This b, the antiderivative of b minus the antiderivative of a. This is how you find definite integrals. This is how you actually find the area under a curve. For example, let's just do one real quick. Let's do a more common one. From 2 to from 4 to 9 of 1 over square root of x dx. We're going to evaluate this. So the first step is we're going to want to find the antiderivative. Right? This may help to write it as x to the negative 1/2 dx. So we do now. We put this in parentheses now. When we're finding the antiderivative, we're going to use the reverse power rule. So we're adding 1 to our exponent and dividing it by that like new exponent. And I'm going to add this line here, 4 to 9. This basically helps us, this is notation for, we're going to plug in 9 into this and subtract when we plug in 4 into this. If you just simplify this out, so x, negative 1/2 plus 1 is 1/2. So it's just square root of x divided by negative 1/2 plus 1, so it's divided by 1/2, which is multiplying by 2, from 4 to 9. Now I can start plugging in. So 2 square root of 9 minus 2 square root of 4. That's what these lines mean. Times 3 minus 2 times 2. We just 4 by 2. That's your area under this curve. 1 over square root of x dx from 4 to 9. I'm also going to quickly cover average value. Let's say you want to find let's say you have like a function here. You're going to find like, what's the average of this? Like what's the average y value that you have? So normally when you're like finding the average of like numbers, then you can just like add them up, divide them by the number of terms. But here, since there's like an infinite number, what we're going to do is we're going to use an integral. So the formula for average value is 1 over b minus a times the integral from a to b of f of x. So this is like our dividing by like n, or how many terms we have when we're like calculating an average, and this is going to be like adding up our numbers, because see, this f of x is like adding up our whole area, and then 1 over b minus a divides it so that we can get an average value. Now let's start going to some more complicated integration. U-Substitution is the chain rule for antiderivatives. And here's how I do it. Let's say you want to take the antiderivative of 2x cosine x squared. Now this looks complicated, right? But you can use u-substitution to help simplify this. What we're going to do is we're going to define u as x squared, so that we can plug in u into here. Alright. Next, this is still in terms of x. See, this is like dx right here. What we need to do is we're going to change it to terms of u, du. But you do, so for the chain rule, you're multiplying by the derivative of your like inside function, which in this case is like x squared, right? But for u-substitution, you're going to be dividing by the derivative. So it simplifies out. So 2x over 2x. So it simplifies out to the integral of cosine u du, which is just sine u plus c. I'll go over trig integrals in just a moment. And now we have our u. Last step is to plug in our original like x's as your u. So substitute x squared, and we get sine of x squared plus c as our antiderivative for 2x cosine of x squared. Now for a definite integral, it's the same process, but you have one extra step. So let's say I want to take the integral from 1 to 2, the area under the curve from 1 to 2, of 2x over x squared plus 1. Right? So the first step, I'm going to define my u as x squared plus 1. A helpful tip when you're defining your u for u-substitution is to choose a value that'll help you get rid of all the x's, so you'll just have u's in the end, right? So I'll start by replacing my x squared plus 1 with u. Now remember last time, I had my like du here. I was changing this integral from terms of x to terms of u. How I did that was I used this u-Substitution, like our chain rule, by dividing it by our derivative, which is 2x in this situation. So these like cancel out. But for definite integrals, one step we don't want to miss is that these bounds, they're in terms of x. They're in terms from x equals 1 to x equals 2. Since we're trying to transfer everything over to in terms of u, it's going to be like u equals. We can't just move 1 and 2 over, but we can use what we've defined here, let u equals x squared plus 1, to help us determine our new bounds. So I'm going to plug in this 1 here. 1 squared plus 1 is 2. 2 squared plus 1 is 5. And now we're going to have this integral from 2 to 5, 1 over u du. Now I'll also go over this integral in just a little bit. Basically, this is ln of u from 2 to 5, which is ln 5 minus ln 2. We're using our integral, using our logarithmic properties. Let's come up to ln of 5 halves. Alright, now here is what I just did. The antiderivative of 1 over x is ln x plus c, because we're doing an antiderivative, not a definite integral, so we need this plus c. We keep this absolute value of x here because ln is not defined for negative numbers. What we do with this absolute value is we make it so it is defined. Basically, we turn a negative number into a positive number, and that just makes it so it works. Because 1 over x works for both positive and negative x values, so our antiderivative should also work for both positive and negative x values. If you leave the absolute value out, and you want to plug in a negative value here, it's not going to work. The antiderivative of e to the x is e to the x plus c. Remember, because deriving e to the x also gives you e to the x. The antiderivative of a to the x is going to be a to the x over ln a plus c. So remember, when we were taking the derivative of a to the x, it was multiplying by ln a. But now that we're taking the antiderivative, we're dividing it by ln a. And here's some trig antiderivatives that are good to know. These ones will be the most important to know. These other ones could be helpful in some situations. It's good to know them either way. The antiderivative of cosine x is sine x plus c. The antiderivative of sine x is negative cosine x plus c. The antiderivative of secant squared is tan x plus c. For cosecant squared, that would be negative cotangent x plus c. For secant x times tangent x, that's secant x plus c. For cosecant x times cotangent x, for the dx there, that's negative cosecant x plus c. The antiderivative of secant x is ln of secant x plus tangent x plus c, and that's the absolute value. Over here, the antiderivative of cosecant x is negative nat log of cosecant x plus cotangent x plus c, an absolute value. These ones are a bit tricky to memorize. These ones don't really come up that often on the AP exam, but these you definitely should memorize. Well, inverse trig antiderivatives. Although there are 6 inverse trig functions, we're only going to memorize 3 here because just remember, like, the derivative arc sine, which is 1 over square root of 1 minus x squared, but for arc cosine it was the negative, right? We're going to ignore this, like, arc cosine. We're going to say, like, oh, negative arc sine x, right? We're just going to take that negative out of our calculations, and it'll still be correct with a lot less memorization. I'm also going to be using a squared instead of 1, because it's not just going to be 1 that'll be down here. It's important to memorize these inverse trig antiderivatives. So for 1 over the square root of a squared minus x squared, that's going to be the arc sine. You can also say sine or inverse sine if you want, same thing, of x over a plus c. For 1 over a squared plus x squared, which, remember, looks similar to this 1 over 1 plus x squared here, right? That's going to be 1 over a arctangent of x over a plus c. And finally, for 1 over x times the square root of x squared minus a squared, that's 1 over a times the arcsecant, the absolute value of x over a plus c. Keep in mind these a squareds, and these are just a's. So let's, here, I'll do an example on the next slide here. Algebraic techniques. So these are just like a review of some algebraic techniques that you may need to use to evaluate, like, some intervals. For example, you can't just use the reverse power rule in this. This is like this fraction here. It's really ugly. What you can do is you can use polynomial long division. X squared plus 3x plus 2 divided by x plus 1. And this is, yeah, a good chance for to review it. Let's do that now. So let's take our first, let's consider our first term, our x, and our first term of this here, x squared. And say we need to multiply x by x to get x squared. And now you subtract x times x is x squared. X times 1 is x. We're going to subtract just like our normal long division. So x squared minus x squared is just 0. 3x minus x is 2x plus 2. Now x times 2 will give us 2x. Next subtract 2 times x is 2x. 2 times 1 is 2. And this leaves us with a remainder of 0. So this is just equal to the antiderivative of x plus 2. So remember that for your polynomial long division is going to be your answer plus your remainder, which we got to be 0, over your what you're dividing by. This is the result of your polynomial long division. This is more used in BC, but I've also seen it pop up as like AB tests too, so it's so important to know. Now that we have the integral of x plus 2, we can use the reverse power rule on that. That's x squared over 2. And then for constant, it's just 2x plus c. And that's our answer. Another technique you may have to use is completing the square. This is also more prevalent in BC. But you still may need to know it. We can try to complete the square of x squared plus 4x plus 8, because you can't just use u-Substitution. That leaves a derivative of 2x plus 4, which doesn't cancel out with anything, so that just wouldn't work. Nope. Okay, so the first step, when we're completing the square, is our x squared plus 4x here. What we do is we take this number, let's write x squared plus 4x here on the side, plus something. Basically, I want this to make it a perfect square, so I can just turn this into a squared value here, but kind of like this. I'm going to take this number 4x, take this 4 divided by 2, and I square it. I get my new number, which is 4 over 2 is 2, 2 squared is 4 again. So x squared plus 4x plus 4 will give us x plus 2 squared. So dividing this by 2 also gives you this number here. That's basically how completing the square works. So I can do now, I can just put this dx on the top, is just an x squared, x plus 2 squared plus 4. Alright, because we used 4 and are completing the square, and now we have 4 left over. So I'll get rid of some of this. Make it clean. This could also be written as the integral of dx over x plus 2 squared plus 2 squared. And now this is in a format where we can use our arctangent integration. And I'll just rewrite that again. Integral of dx over a squared plus x squared. It's 1 over a arctangent x over a plus c. So it's like x plus 2 here. Normally what I do is use u-Substitution, but since our derivative is 1, then we don't really have to. We can just sort of treat this as like an x, since our derivative is 1, right? So we do 1 over a. So we have a squared here. The a squared is 4. But that's actually 2 squared. So I'd put 2 here. Arctangent of x plus 2 over 2 plus c. And that's that answer to this problem right here. Okay, that's all for this video. I'll see you in part 4, where it started on differential equations.